This is the long-awaited for video of number 3 of 7.1 to 7.10 review. It's a free response. And you have this equilibrium system of a yellow HBPB plus and blue BPB. This is bromethymol blue, and it's a bromophenol blue. And if you bubble into it, you actually make it turn yellow because the carbon dioxide in your breath makes an acid, carbonic acid, and it causes the blue to turn yellow. And so it's yellow in more of an acidic solution. And when you add a base to it to deacidify it, you'll turn it back to blue. So the equilibrium expression is here, letter A. And that's number, I have it written twice, don't I? There's letter A. Number B, at which wavelength are photons with the higher energy absorbed? And I want to say use equations. So you have an equation sheet that has two different equations that you can use. And I want to just point out what they are. Actually, let me see. Yeah, there they are. They're right here. These two equations right here. So when you are making a statement about a relationship, then you need to use an equation to justify that relationship. So the question is higher energy, and we're going from nanometers, which is a wavelength. So we're going from a wavelength to justify higher or lower energy. Blank, higher or lower. And if you look at it right here, you see that there's an equation that relates energy to this V, which is really new. Like what's NU, what's new? It's frequency. And then you have another equation that relates frequency to wavelength. So you have to bridge the gap from wavelength to first frequency and then frequency to energy. So I'm going to just say this again. When you are justifying direct or indirect relationships, you have to use an equation to justify that. Okay, and that's going to be really the evidence. That the E part of your CER will be equations. The claim is that the 350 nanometers is a higher energy. So the shorter wavelength is a higher energy. So let's use our equations to justify. 350 nanometers has a higher frequency because F, frequency, and wavelength are inversely proportional. So I would say this, instead of frequency, since they use new frequency, and so you could go ahead and in my evidence here, I should show, well, why? How do I know they're inversely proportional? Well, we've got this equation that's given on the equation sheet. And so we could see that if C is a constant, if wavelength goes down, V goes up. So if C, oh no, we don't say if, we just know C is a constant. C is a constant. So as wavelength decreases, our frequency, and I would write out those words, not just use will increase. I would use not just the symbols, but actually write out the words. So I made a claim here. Well, I made a claim within my evidence that frequency and wavelength are inversely proportional, but I'm backing that up with an equation that they give. So here's just the tip. If they spend ink and energy giving you an equation, use it. And here's where they want you to use it. Okay, so we can use another equation. So now that we've gone from our relationship between wavelength and frequency, we can say our rationale then, our reasoning, as the frequency increases, and again, they don't use frequency, they use nu. So I'm just going to have it as nu increases, as frequency increases, the energy will increase because here we see H is a constant. H is E over, I just want to use F for frequency. They use nu. There it is. H is E over F, nu. See, they give you that right there. H is Planck's constant. They tell you that right over here. So you've got two constants. You've got C and you've got Planck's constant. So H is a constant. So as nu increases, as your frequency increases, your energy increases. So the bottom line here is that you can't just make a claim of, oh, shorter wavelength has a higher energy, which is true, but you have to prove why it's true. Okay, use equations. So keep in your mind, and it's been a while since we've done wavelength and frequency, but that's from, I think, topic 1. Topic 1. Okay, letter C. Based on the diagram above, is the forward reaction endothermic or exothermic? And so based on that diagram above, okay, so what do we see? At a higher temperature, you get a bigger peak of BPB, which is a product. So at a higher temperature, we're getting more products. So I said endothermic, and it's perfectly fine if you do your E first. What I just said, a higher peak for the product at a higher temperature. So, and if you have to do your rationale first or your reasoning, an increased temperature favors the endothermic direction, right? If you increase the temperature, you're going to want to cool it off by running the reaction to cool it in order to remove the added heat stress on the system. So it's endothermic. Number D is just reading the graph, 0.4. Just read up, 0.4. Letter E, student measures the absorbance of an unknown. He leaves some water in. The water will decrease the absorption, so it will appear to have a lower concentration. So here's my CER way of doing it. I kind of wrote that out, like in my thinking, and then I reformulated my response in the CER. The molarity is too low. The molarity compared, and maybe I shouldn't say too low, I should say the molarity, use the wording that they use. Molarity compared is lower compared to the actual. Molarity lower, and of course don't write in. So use the prompt wording, the actual BPB. Just show that you're making that connection. The evidence is that there's residual water that's diluting the solution. And the reasoning is that, and here's the chemistry, here's the science, right? Absorption and concentration are directly proportional. So when you have a lower absorbance, you're going to appear to have a lower concentration. A lower absorbance will then appear as a lower concentration. So use the science behind it. Why, the concentration and absorbance connection. Letter F, determine the half-life. It's 1 hour, and they said include units. So just look right there. There are your units. 1 hour. So how long does it take to cut in half? And explain how the absorbance and time data are consistent with a first order. The half-life remains constant. Look at your next half-life. From 0.4 to 0.2, it's another hour. And from 0.2 to 0.1, it's another hour. So the half-life remains constant, which is characteristic of a first order. That's an RX, first order reactions. And look, they give you another equation for that, right? That's right down here. K is a constant. And so is 0.693. So I rewrote that. You can see as if this is for a, and remember this equation is for a first order. If K is a constant, you can rearrange this. If K is a constant, which it is, if you have the same half-life, you're always going to get the same K. So in order for K to be a constant for a first order reaction, the half-life has to be constant. Letter H, explain in terms of particle collisions while the half-life decreases. So if you increase your concentration of one of your reactants, you're going to have more collisions. Therefore, you're going to have a greater rate. And yeah, don't just write sentence fragments like this because you can flesh that out a little bit more. The half-life decreases a greater rate. So to decrease the reactants in what you're measuring the absorbent, or actually what you're doing is, your absorbance is going down. So to decrease the reactants by half takes less time. Takes less time. So if you just stop here, you wouldn't get the point, I don't think, because they say, why does the half-life decrease? They don't say, does it go faster or slower? So take it all the way to the prompt of what they're saying. More collisions mean a greater rate, and the greater the rate, the less time it takes to cut your concentration in half. So connect it to the thing they're asking about. Do you see what I'm saying? So they didn't say, would increasing the concentration cause the reaction to go faster or slower? They said, what happens to the half-life? Letter I, when the OH minus is changed from 0.1 to 0.4, does the magnitude of delta H, the enthalpy change, increase, decrease, or stay the same? Well, here's the definition of enthalpy change. This is kilojoules per mole. Okay, so if you increase your concentration of one of your reactants, you're going to cause the reaction to go faster, or you're going to get more product stoichiometrically, which means for an endothermic reaction, you're going to decrease by more kilojoules. But so your numerator of this will be a greater number of kilojoules, but you're also reacting a larger number of moles. So the delta H of reaction remains the same. So keep in mind that these delta H's, these enthalpies are not, they're good for the reaction. You can put in different ratios of the reactants, and you're going to get the same delta H of reaction. You don't always have to start with this amount of that and this amount of that. If you up one of them, you're just going to make it maybe faster or slower if you decrease it, but you'll have the same overall number of kilojoules per mole of reactant that you're reacting. As long as you have enough of the other one that you're reacting, we're assuming that the other is in excess. Okay, the next one, this is a mammoth question. In order to prepare, okay, so this is just a molarity. Let's make a molar solution, and we want to make 0.1 molar. And so it's just 4 grams in 1,000 mils because it's 40 grams per mole so the molar mass of NaOH is 40 grams per mole. That's the molar mass. So you need to put 0.1 moles in 1,000 liters. 1,000 milliliters. So 0.4 grams in a 100 mil would work, or 4 grams in 1,000 mils. So think about what I need: a 0.1 mole, and in 1 mole, it's 40 grams. So it's 4 grams per mole, 4 grams in it is a 0.1 mole. You put 4 grams in 1,000 liters is a tenth of a mole over a liter, which is 0.1 molar. So that's just mixing up a molar solution. You could also take they made too concentrated. You could dilute it by a factor of 10, but either one of these mixed up will give you a 0.1 molar solution. Swirl it or stop or invert. I don't know. That letter K was kind of weird. Swirl it. If you have some undissolved solid, just swirl it. Or you can stop or invert the whole volumetric flask. Moving on. Okay, so remember, the larger the Q, this is the C. This is the lowercase c, and the greater the specific heat, the larger the specific heat capacity. That's what this is called. The more the more heat it can absorb without changing temperature. It can absorb more energy and increase with a smaller delta T. At a smaller delta T. So the same amount of energy, it'll have a smaller delta T. So the question is, what is the question? Assuming the enthalpy change, okay. Would the temperature change in solvent X be greater than, less than, or equal to? In X, it's going to be greater than. And justify your answer. Your evidence, the E, would be, here's my E. And I should say just a C. It would be, oh, here's my C, my claim. My claim, it's greater than. And the evidence is that X has a smaller C. And then my rationale is using the equation. And see, here's another, use the equation that they give you. Delta T is Q over MC. C for X is smaller, and it's in my denominator, so it's going to give me a larger delta T. Is that the end of this problem? Yes, thank goodness. Okay, lunchtime for me. Oopsie, don't look at that. Yipes.